Good afternoon. So my first confession is I changed the title. We ran into some challenges since we submitted the abstract, and so instead of being Plasticity and OOF, it's going to be Towards Plasticity and OOF. And hopefully I'll be able to describe to you some of the challenges and the benefits of our architecture and sort of Pythonic approach in meeting some of them. So the approximate outline is I'm going to start with a description of the OOF code, who its intended audience is, what we thought we were doing when we wrote it, and how it works. I will give a successful example of extensibility of the code, which is not plasticity, but sort of is fake plasticity, and then I will describe some of the challenges. And also, I'd like to place OOF in the SciPy context. I think this is something that we've kind of been bad at, and our engagement with the SciPy community has been a little bit problematic sometimes. So I want to make sure that I get that. Hopefully I'll have enough time to get there and speak clearly about that. So the scope of the OOF code is material science. It's a finite element modeling code, which I realize now is on the second slide. The length scale at which we want to operate is sort of at what in material science is called the mesoscale. It's in the continuum regime where microstructure is important. We're not doing quantum mechanics. We're not doing atomistic modeling, and we're also not doing sort of full parts. We're not modeling bridges or battleships or things like that. Although, in fact, it's important maybe to be clear that there's no intrinsic length scale in the OOF code. If you have a nanostructure that you think fits a continuum model and you have a constitutive model that works for it, you can use OOF to model it. It's interdisciplinary, as is all of material science. There's chemistry, there's physics, there's electrostatics, electrochemistry, that sort of thing. And we're focused on structure property relationships. It is an axiom of material science that structure controls properties. And structure property relations are how you quantify and describe those. And the kind of basic questions we're interested in are the forward problem of material science, which is given a structure and some constituent properties, how does that control the aggregate properties of the system? And then the sort of inverse problem of material science, or the materials design problem, which is for some given constituents, what's the right structure to give good properties? There are lots of really good FEM codes out there. But we think that there was a hole in the tool set that we were able to fill. Many FEM codes make it difficult to mesh irregular microstructures. This is actually the real original motivation for the OOF code. One of the investigators at NIST tried to use the Abacus meshing tools to mesh a microstructure that was pretty similar to the one that's in the picture. That's, I think, silicon nitride. And it took days and was insanely hard, and he just thought there's got to be a better way, which is, you know, the SciPy community I think understands this sort of scratching an itch motivation for making software. Other FEM codes can also be hard to extend. Sometimes, almost none of them really speak the language of material science, so they're not addressed directly to the audience that we're addressing. And some of them may do more than you need, which is a problem if you have to pay for it with money or time. It may also be that there are ones that are free that do less than you need. I've become aware in the past year or two of a number of actually quite good Python FEM modules. Some of them I've looked into, and I found that, in fact, our niche is still ours. I don't know how long that will be true. Commercial codes in particular also can be have a black box character to them that makes them hard to validate if you're interested in reproducibility. That may be a problem for you. So this is, so I should warn you that there are going to be more equations than this. I promise I'll walk you through them. It won't be too bad. The general mathematics of material science as we view it is that you have some kind of flux, and it's dependent on a field, phi, and so the field is the thing that you can manipulate, and the flux is what happens when you do that. And there's generally an equilibrium equation of some kind that says that the divergence of the flux is equal to some applied force or is equal to 0. And so the top equation there is just this equilibrium equation. It's schematic. And the equation in the yellow box is what we call the constitutive rule, and it tells you how the field relates to the flux. And in this case, this is sort of, so this kind of structure is common. Diffusion looks like this. Thermal conductivity looks like this. Elasticity looks like this. This basic scheme, which is what we started with, actually covers a huge amount of ground in material science and in the kinds of modeling that we want to do. It's a little bit more complicated if you add time dependence and dynamics, so this is a little bit more complicated version of the equilibrium equation where field first and second derivatives might matter, so you may have oscillating solutions in your field, and the flux might depend on field time derivatives as well as on the field itself. And I didn't say, but should have, that the yellow box stuff, the constitutive relation, is really where material scientists live. If you ask them about a system, they will probably describe it in terms of the constitutive rule, maybe in terms of the microstructure. And again, so I've reiterated here that typical fields are displacement for elasticity problems, temperature for thermal conductivity problems, concentration for diffusion and maybe reactivity problems, and the fluxes are mechanical stress, heat flux, chemical flux. So this is the way we discretize the system. The takeaway from this slide isn't necessarily the details of the discretization, but that there is one, and that in order to construct it, we express the field, which is a continuum field in space, as a sum of some basis functions, and the equilibrium equation then, so there's an implicit piece that's actually missing from the slide. If you take the constitutive rule, which is a function of the fields, to be a function of these basis functions, and then do the equilibrium equation, what you get is the thing in the blue box, which is a giant linear system. The left-hand side, in spite of the various notational flourishes on there, is really a big matrix that multiplies a vector of phi i's, and the first term rather, and the second term is the discretized version of the force. I'm belaboring this a little bit because it's going to be important later for the plasticity part. So the OOF use case or workflow, the user is an expert in material science, but he is not a numericist, and he may or may not want to code. He or she may or may not want to code. And the steps that the user has to go through to make use of the OOF code is, first they have to bring a microstructure to the table, and some constitutive rules. They need to segment the microstructure and identify which regions of the system correspond to which constituent phases. Then they can use OOF tools to construct a mesh that is roughly congruent with the segmented image, so that the boundaries between elements in the mesh correspond to boundaries between regions in the microstructure. Then add the math and physics, could solve the finite element problem with the appropriate boundary conditions, and then get some results. We have a conceptual framework that is sort of container-like. We have, on the one hand, materials, which are collections of properties, and properties are mappings from fields to fluxes, which can be pretty much arbitrarily complex. So that's one piece, and the other piece is a sort of hierarchy of containers. The outermost container is a microstructure object, which is sort of document-like, and it can contain one or more images. From the microstructure, you get what we call the skeleton, which is the finite-element geometry exclusive of the physics. And then for each skeleton, there is one or more mesh objects, and the meshes reflect the skeleton geometry and contain the physics. They have the equations and the constitutive rules and so on applied. So the segmentation process, in slightly more detail, OOF provides a number of tools for modifying the image. You can blur, you can despeckle, you can do various kinds of edge detections. We have some nonlinear diffusion models in there. We actually have one guy on the team who is a specialist in image segmentation who is developing more sophisticated tools. You can also manually select regions if you find that automatic tools aren't working for you. You can identify and define pixel groups, name them, and do sort of constructive geometry with them. You can find intersections and unions and combine selections in various other ways. So again, this is partly based on who we think our audience is. The OOF user is really good at assessing a good segmentation. If you give them a segmentation, they will say yes, they can say quickly, yes, that's right, or no, that's not right. But they may not be able to, they're not themselves image processing experts. So the idea is to provide them with a variety of tools that can get them where they need to be, and it's up to them kind of to recognize when they've gotten there. For the finite element geometry, the philosophy is pretty similar. We start with a segmented image, and we overlay it with typically space-filling regular mesh. And then again, we have tools to adapt the mesh. This actually can be fully automatic for some classes of microstructures. We have a sort of mesh button that actually does a pretty good job most of the time. If that doesn't work, we do have ways you can refine the mesh. You can anneal using a fake energy function, which will be in more detail on the next slide. And also, to assist with assessment of the quality of the mesh, we have quantitative measures that you can ask about. You can ask about the homogeneity of the mesh, which is just an element is homogeneous if it only overlies one category on the image, and the regularity of the elements. Elements are regular if their if their aspect ratio is approximately 1. For finite element evaluations, that helps with convergence of the global finite element problem. So, and again, the UF user is a material scientist. He's not an expert in mesh construction. He probably knows a pretty good mesh when he sees one, but even if he doesn't, the quantitative measures that we provide can help them out in figuring out whether they've gotten where they need to be. So, and as I said, we've gotten farther with automating this than we have with the segmentation. We have a quantitative rule for assessing the global mesh quality. It's a fake energy. It's just a function that for inhomogeneous elements has large values, and for homogeneous elements has small values, and for high aspect ratio elements also has large values, and for aspect ratios close to 1 it has low values. You just add these things up with a weighting factor that allows you to choose between whether you think homogeneity or aspect ratio is more important. And when you do the simulated annealing, this is the energy function that the simulated annealing system is trying to minimize. In the next step in the workflow, you add the math and physics. Here, I think we do a pretty good job of speaking the language of material science and addressing the needs of our audience. You select the fields and fluxes. You select the planarity. So you've seen all these images are 2D. The current UF release is a 2D code, but the constitutive rules have been from the beginning fully 3D constitutive rules. You also select the element order, and we have iso and sub and superparametric elements. Those of you who are experts in finite element will know what that means. Others can ask me later if they're interested. We have a wide selection of constitutive rules, lots of built-in properties, mostly the obvious ones, linear elasticity, linear thermal conductivity, piezoelectric, and several couplings, thermal expansion, piezoelectricity. The ability to save and share properties, so if you find that you have a particular set of parameters that really well models the thing you're kind of doing, you could save it and use it again in other computations. Everything is open source, so it's sort of the ultimate in extensibility if you're willing to put in the work. And this is a case where having a Python API has been particularly useful. The constitutive rule API is at exists at several levels, but in particular there are Python hooks for everything. Here we think the UF user is an expert in the constitutive rules, at least in the equations for the constitutive rules. They may or may not be coders, but if they are, or if they can hire coders, or if they can talk to us, we are coders, we can get them there. So I already talked a little bit about this. There's an extension framework. This does put some constraints on the system that actually have bit us a couple of times. User-supplied properties and constitutive rules can be arbitrary mappings. So there are some places where we were tempted to take shortcuts and where sort of more ordinary finite element codes do take shortcuts, but we can't because we don't know for sure that the mappings are going to be regular or that they're going to have the same conjugacy or that they're going to obey various kinds of sort of normal constraints. In particular, it's common when you're doing 2D problems with 3D constitutive rules, all the finite element books do the same thing. They say, oh, you just modify the constitutive rule so that the out-of-plane couplings go away. We can't do that because we don't own the constitutive rules. So we do planarity, either plane flux or plane field constraints differently by way of a global constraint that is imposed weakly on the whole system. There are some hooks that if you, so one of the downsides of this is sometimes it can be numerically slow to not make these assumptions. If, for example, you can't use certain high performance iterative solvers if you don't know your matrix is going to be symmetric. But so there are hooks where users who write constitutive rules can supply some metadata and make promises about how they're going to interact with the system, and if they supply the metadata and if the promises are in fact fulfilled, then higher performance conjugate gradient methods, for example, will work. So the linear algebra follows more or less the same philosophy. We have a bunch of high performance algorithms that we have looked at and adapted, and we've selected sensible defaults for most classes of problems. Again, the UF user is not an expert on selecting solvers. We think we've made some good choices for them. They're conservative in the sense of bias towards accuracy and away from speed. And that's how, so again, the user doesn't have to bring this expertise to the system. All right, so this is, for example, for the generalized minimum residual method, which doesn't require a symmetric matrix. It has this Krylov piece, and it's hard to know how to pick that. But you don't make a huge mistake if you get it wrong, and if you pick sort of 10% of the size of the matrix, it seems to work pretty well. We have a local graphics window where you can do interactive assessment of the data. You can look at statistics on, for example, the fields or the fluxes that are inside the system. You can find outliers. You can take averages. You can take averages within certain materials. You can do integrals on the boundaries to find out what the aggregate forces are, and it's relatively easy to add new methods. This is one of the things where actually it's kind of hard to know when to stop, just because we have the mesh and there's a lot of mesh-specific things you can do. You know, there's always sort of every algebraic possible combination of every output is sort of nominally in scope, but on the other hand, we don't really want to write an infinite amount of code. So we sort of made some choices and stopped. So the architecture, which is relevant maybe to this audience, it's written in a combination of Python and C++. We don't make a huge amount of use of what are now standard SciPy tools because they were not standard SciPy tools when we were making those choices. We were using, as you can see, Python for the high level. It's very flexible, it's dynamic, it allows for rapid prototyping and rapid refactoring. We use C++ for a lot of the sort of heavy lifting and computational work. There's tons of libraries, the executables are fast, and we use Swig to bridge the two. A major advantage of Swig, I actually haven't heard much about Swig at this conference, it used to be more commonly used. Major advantage for us of Swig is it allows us to move the Python C++ language boundary around according to our requirements. We have done this several times where we'll run into something where performance just isn't good enough and we need to move a bunch of Python code down to C++, and we can do that. We just write it in C++ and wrap it, and the whole top-end architecture all still works. I think we've gone the other way a couple of times too, where we found something that just isn't mature enough. We really need the flexibility of Python, so we can bring it up into Python and just swig the lower level things. I was making this slide and I noticed actually the line count has actually gone down a little bit since the last version. I think that's some kind of maturity, I'm not sure. Runs on Unix-like systems, Mac OS X and Linux, depends on some stuff. So now I've just seen my little clock here and I know what the time is. 2.1.11 released May of 2014, has a number of features that are listed there. And I do want to get to the plasticity, so I'm going to blast past the 3D stuff and maybe give short shrift to the fake plasticity. So the thing about plasticity is what happens when you, particularly in metals, for example, if you bend a metal and then let go and it stays bent. That's plastic deformation. So we had a fake plasticity example that I'm not going to spend a lot of time on, except to point out maybe that, so this is the constitutive rule, and the point of this is not necessarily to understand this equation in detail, but to realize that sort of everything in here is a nice analytic function and everything's all nice and differentiable. That's what made this pretty easy. It is an inverse, kind of an inverse problem we had to do Newton-Raphson pointwise. So this is the microstructure that I invented for this. It's the main feature of this is that the phase fraction of the particles is exactly 50%. This is the mesh, and here's an example. It does what you think. If the plastic part is in the matrix, it's softer than if the plastic part is in the particles, because the weak strain can percolate through the system. So we were emboldened by that. This is a thing, I actually had never heard of Ramberg-Osgood elasticity until about 3 years ago when I learned about it in an informal meeting with a NIST visitor. And I thought, okay, that should be easy, and oof, let's do this. And it actually was. The hardest part was finding, he had given it to me in sort of a scalar form, and finding the actual paper that had everything with all the full tensor notation took longer than implementing it in oof. So classical plasticity, which is what I'm going to talk about here, is this process where you bend something and it stays bent. So the curve that's on there is a sort of it's a cartoon of a load displacement or a stress strain curve, and the red curve is the loading part. You apply some kind of force or tractions to the boundaries of the thing, and what happens is after a while the thing starts to move a lot with little additional force. That's that big red plateau. And then when you let go, it comes back down the blue curve and ends up in a different place than where you started. That's the permanent deformation. And the little green arrow at the bottom there is the residual strain or the plastic strain. So the way this is described in material science, classically speaking, is one imagines that there is a surface in stress space, and so these are roughly the same arrows as on the little cartoon there. The arrow that goes up and to the right in the stress space picture is the loading thing. What happens is you reach what is called the yield surface, and then as you add additional load, the strain gets split up into the plastic part and the elastic part. The plastic part is the part that doesn't go away. And so what happens is, so the red arrow that's following, sort of tangent to the surface, is the evolution of the elastic state, and the green arrow there is the evolution of the plastic state of the system. Now, if you're really paying attention, you'll notice that it's a plastic strain that I was talking about, but this arrow is in stress space. I am in fact cheating. I'm not going to explain that unless somebody asks. And then when you unload, the stress is relieved, and the stress goes all the way to 0, but as you remember from the cartoon, the plastic strain is still present. And the equations, which again, you're not expected to understand the equations in detail. The first line of equations shows that there is this separation, and the last one of those is just the equilibrium equation. The second one is some evolution rules just to prove that they exist and that there are a lot of parameters. The Rij function is the flow rule. The yellow equations are the important equations. And this one actually kind of is interesting because if you think in code, this is an if statement. Right? So gamma is a parameter that tells you roughly how much plasticity is happening, and the y thing is the yield function. And so what those two together say is that gamma is greater than or equal to 0, which is to say that plasticity could be happening, and the other one says that the yield function is less than or equal to 0, which means you're either inside it or on it. And then the third one says that the product is 0, which means that at any given point in space, only one of the first two things is happening. Either you're inside the yield surface, or there's some gamma, and if you look at the rules above, if there's some gamma, then the evolution rules are all turned on and things are happening to the plastic strain and to this Q parameter, which is a hardening parameter, which I didn't introduce. So there's an if statement and there's some inequalities. So the idea is this is in stark contrast, starker than we appreciated, in fact, to the Ramberg-Osgood thing, which looks complicated, but actually turned out to be very simple. So here is the math to FE reprise, which does not have the inequalities in it. So the question is, if you want to implement this, where do the inequalities go and what do you do? And the answer is, they're at a slightly higher level. What you actually do to solve the plasticity problems of this type, excuse me, is given the accumulated plastic strain that you have from all your prior operations, you solve the equilibrium equation as though the system were elastic, then you survey the system and look for places where the yield condition has been violated, and locally, point-wise, you increment the plastic strain at each of those points so that the yield condition is satisfied locally, and then with that accumulated plastic strain, you go through the system again, and you keep doing this until the fully elastic iterations get you that the yield condition is satisfied everywhere. And so this is clearly sensitive to the level of time discretization. But the good part, and it's quite complicated, it completely breaks our workflow. There are two pieces of good news. One is that because we own the code and because it's Python, breaking the workflow actually isn't so bad. And the other thing is because we solve this at a very high level of generality, consistent with the level of scope that we want for the OOF program, it looks like we might get other kinds of inequalities out of this for free. In particular, surface interactions are like this. If surfaces exist but can't interpenetrate, that's also an inequality constraint. So we might get that for nothing, we're not sure. So there's a generalization of plasticity called crystal plasticity. OOF is a part of the Materials Genome Initiative, and our principal goal is to complete our solid mechanics suite, including crystal plasticity, so we can look at forming problems that depend on texture. Texture is the relative orientations of the crystallites that typically occur in metals. And we also need to ensure that large strains are being handled correctly, which is, we think they are, but we need to prove that they are. So my first conclusion is what we've learned from this is Plasticity is hard, that's not on the slide, but the other thing we've learned is that actually the UF code actually is a versatile platform for implementation of these kinds of real space microstructure sensitive materials models that are of interest to our community because we own the code and because it's Pythonic and because it's easy to use the relevant abstractions. We're actually able to make the kinds of changes we need to do even when they're large and terrifying. The thing we have a problem with is we probably don't move fast enough. We really do. We really do have a problem with slowness. And to place the thing in the SciPy context, we've had a number of interesting conversations here. I think the first keynote covered some of it, and Fernando Perez covered some of these things. That SciPy is not just Python and some tools. It's a way of thinking about computational science. We think we share this with the community. We care about code. We care about building tools. We care about good abstractions. I think we are people like us. The educational thread at the conference also, and some of the comments that people have made bear out that actually this approach to code within the scientific community is far from obvious. This is a special place, this is a special community, and we're pleased and proud to be part of it. And I think, as the other part says, we derive a lot of value from this community. That's in part why the National Institute of Standards and Technology was a sponsor this year, although I emphasize that I personally had nothing to do with that. I'm proud of it, but that's all. You're right, I did. So this is the UF development team. You may be astonished to learn that I did not, in fact, do all this by myself. Thank you.